Hi folks, we're going to take a look at number 11 now from page 128. So they give us this height versus time function. So h in meters, t in seconds, and it's representing a ball that's thrown upwards and then falls back down to the ground. Okay, so this still qualifies as motion in a straight line because you're just looking at the ball moving along this vertical line. Okay, so notice here they decided to use h instead of S for position. I guess makes sense for height. Okay, so let's see the first thing they're asking us for. So they want us to calculate the ball's initial velocity. So first we'll find the velocity function. Okay, and of course the velocity is just the derivative of the position function. Okay, so that's pretty straightforward. So negative 10t plus 25. Now notice here, most of you have studied physics, and you should recognize this negative 10 as being very close to negative 9.8, so an approximation for the acceleration due to gravity. And if you were to take the second derivative of h, you'd just be left with negative 10, so that, constant acceleration due to gravity. Okay, but in this case here, we're looking for the initial velocity, so we're looking for v at 0. So negative 10 times 0 plus 25 equals to 25 meters per second. Okay, now here, since our values here have context, we have to put in units. Now again, for those of you who've studied physics, you should recognize that initial velocity as what should be in front of your t variable here. Okay, so it's negative 1/2 t squared plus v naught t, v naught representing the initial velocity. Okay, so this is all giving us stuff that we should expect based on what you studied in physics. Okay, so let's go to B. So B says calculate its maximum height. Okay, now at this point here, we don't have any official calculus that we can use to determine that maximum height. And since this is just a quadratic, well, we can use some of our old methods. So I could certainly complete the square, but here, this is pretty easy to factor. Okay, I'll just factor out the negative 5t, and I'm just left with t minus 5. And so my zeros are at 0 and 5. And I know that the maximum is going to occur right in between those two, so at 2.5 seconds. Okay, and that's by the symmetry of a parabolic function. Okay, so if I'm looking for the maximum height, I just have to take h at 2.5. So that's negative 5 times 2.5 squared plus 25 times 2.5. And unfortunately, I just realized I don't have my calculator here, so I'll try to do this in my head. So this is 6.25. So this is going to be negative 30. And 5 times 0.25 is 1.25, so 31.25. Plus 25 times 2 is 50, and 25 times a half, 12.5. So 50 plus 12.5 is 62.5. And that's exactly double that one there. Okay, so that gives me 31.25 meters. Okay, so in this case here, we were able to determine this answer without using any calculus. Okay, so let's go to part C, and part C asks, when does the ball strike the ground and what is its velocity at this time? Okay, so again, that first part, I'm not going to use any calculus. I just need to figure out when this ball is going to strike the ground again. So essentially, I need to determine when the height is equal to 0. Okay, and the height's equal to 0. Let's solve this equation. Negative 5t times t.5, t minus 5, sorry. So we have it at t equals 0. So basically this tells us that the initial height was 0, but that's not what we're looking for. Okay, the other moment at which it's at 0 is at 5 seconds. Okay, so it hits the ground at 5 seconds. Okay, and they ask us the velocity at that time, so we're just going to stick this into the velocity function. Okay, so v at 5 is just velocity functions up here, so negative 10 times 5 plus 25. Okay, and so here we just have negative 50 plus 25, so negative 25 meters per second. Okay. Now this is not surprising because presumably they're using downward as negative direction. So since it's hitting the ball as it's traveling in the negative direction, the derivative should be negative. Okay, so again, just to recap here, we solved this problem by using some calculus, but also by using some of our traditional methods for working with